In the grand tapestry of the cosmos, there exist regions of utter darkness. We call them black holes, the universe's ultimate mystery. Hiding in plain sight were these gravitational behemoths. A black hole is what remains when a massive star collapses. It punches a hole in the fabric of space-time, a one-way door in the universe. Not even light can escape its grasp. It is a fundamental part of our human desire to know our place in the universe. The story of the black hole is a testament to human curiosity and our relentless pursuit of truth. It is a story that is still being written, adding another layer to this cosmic puzzle. How do you find something invisible? You can't see a black hole directly. Its gravity consumes all light. Astronomers hunted for a ghost, predicted by math, but hard to verify. They shifted to looking for its influence on the universe. Stars behaved strangely, orbiting empty space at high speeds. The region outside a black hole, the accretion disk, is highly energetic. Gas and dust spiral inward at near light speed, creating friction and heat. Telescopes detect this glow, a final cry before matter disappears. This evidence built an irrefutable case for black holes. They transformed from theory to a tangible part of our cosmos. Black holes hold a primal fascination. They are cosmic monsters, representing the unknown. This taps into our love for stories of mystery and adventure. The name itself suggests a bottomless pit or an end to everything. Science fiction uses them for time travel and survival tales. We're drawn to extremes, and black holes are the densest objects we know. They challenge our understanding, forcing us to question reality. What lies inside? The singularity breaks our laws of physics, signaling incomplete theories. Born from dying stars, they reside at the heart of galaxies. Studying them connects the life of stars to the fate of galaxies, captivating scientists and the public. Our universe is a place of staggering contrasts. We live on a gentle, life-sustaining planet orbiting a stable, nurturing star. The cosmos is overwhelmingly a realm of extremes, a place of cataclysmic explosions, unimaginable temperatures, and crushing pressures. Existing in a category all their own are black holes. They represent the most extreme environment the universe has to offer. Near a black hole, gravity becomes the supreme, unopposed force of nature. It is a force so powerful that it warps the very geometry of space and time around it. The accretion disk of a supermassive black hole can outshine all the stars in its host galaxy combined. This universe of extremes forces us to abandon our common-sense notions and embrace a more abstract, more mathematical understanding of reality. To understand black holes is to accept that the universe operates on principles far stranger than our limited human experience would suggest. Our understanding of black holes is a magnificent journey that begins with Einstein's theory of relativity in 1915. He proposed gravity as a curvature in space-time caused by mass and energy. Shortly after, Karl Schwarzschild found a solution suggesting that if mass is compressed enough, it would create a region from which nothing could escape. The term black hole was coined later by John Wheeler. Astronomers realized that massive stars could collapse under their own gravity, forming black holes. This led to the search for observational evidence. The discovery of Cygnus X1 provided the first strong evidence for a stellar mass black hole, marking a new era of discovery. Today, black holes are a cornerstone of modern astrophysics. Each new discovery seems to open up a dozen new questions, making the black hole the ultimate cosmic question mark. We now know that black holes come in a range of sizes, from stellar mass to supermassive giants. The Event Horizon Telescope gave humanity its first ever direct image of a black hole silhouette in 2019. Meanwhile, gravitational wave observatories have opened an entirely new window onto the universe. In the parts that follow, we will embark on a detailed exploration of these cosmic enigmas. The black hole is a profound cosmic question mark, and our journey to find the answers is just beginning. The idea of an object with gravity so strong that even light cannot escape is quite old, predating Einstein's theories by more than a century. In 1783, John Michel first conceived of this possibility. Wondering if a star could be so massive, that its escape velocity would exceed the speed of light. He called these hypothetical objects dark stars. Einstein's general theory of relativity completely rewrote our understanding of gravity. Gravity, Einstein showed, was the curvature of space-time. The dark star was reborn as a black hole, an object that fundamentally trapped a piece of the universe, sealing it off from the rest of us forever. For a black hole to form, nature needed a mechanism to compress a star's mass into a tiny volume. A star exists in equilibrium, with gravity pulling inward and nuclear fusion pushing outward. Eventually, the star exhausts its fuel. Gravity wins and the core collapses until halted by electron degeneracy pressure, forming a white dwarf. In the 1930s, Subrahmanyan Chandrasekhar discovered a limit. Calculating relativistic effects on electrons in white dwarfs, he found that if a core's mass exceeded 1.4 solar masses, electron degeneracy would fail. This Chandrasekhar limit meant gravity would be unstoppable, leading to further collapse and potentially a black hole. Massive stars, at least 8 times the mass of our Sun, live fast and die young. They develop a layered structure, forging heavier elements until they produce iron. Iron fusion consumes energy, causing the core to collapse in a fraction of a second. The implosion occurs at incredible speeds until halted by neutron degeneracy pressure, forming a protoneutron star. The outer layers rebound, creating a shockwave and a torrent of neutrinos, triggering a core collapse supernova. The explosion rips the star apart, briefly outshining a galaxy and scattering heavy elements. These elements seed new clouds of gas and dust for future stars and planets. What remains depends on the initial core mass. The fate of a stellar remnant determines whether a neutron star or black hole is born. If the initial star was 8 to 20 times the mass of our Sun, the collapsing core will likely form a neutron star. However, if the progenitor star was more massive, exceeding the limit that neutron degeneracy pressure can withstand, a black hole is born. The core continues to shrink, crushed by its own gravity, forming an event horizon. A stellar mass black hole has been born, typically with a mass between 3 and several tens of times that of our Sun. In some cases, for the most massive stars, the collapse may be so swift and powerful that it results in a direct collapse, where the star simply vanishes. Stellar mass black holes are well understood, but the cosmos holds another puzzle: supermassive black holes. These giants reside at the centers of nearly all large galaxies, including our Milky Way, and can be billions of times the mass of our Sun. Their scale challenges formation theories. Growing through accretion, they consume gas, dust, and even stars. But scientists struggle to explain how they reach such sizes so early in the universe. This suggests they started from larger seeds. Perhaps the first stars, population 3 stars, collapsed directly into black holes, providing a head start for growth. Quasars, extremely luminous active galactic nuclei powered by supermassive black holes, challenge our understanding of the early universe. Their light, traveling over 13 billion years, shows them as infants in cosmic time. The direct collapse black hole model suggests vast gas clouds under unique early universe conditions could have bypassed star formation, collapsing directly into massive black hole seeds. Future telescopes like the James Webb Space Telescope may find evidence of these events, unlocking the origins of supermassive black holes and the first galaxies. Regardless of how the initial seeds formed, whether from the first stars or direct collapse, it is clear that another process must play a crucial role in building up the most massive black holes we see today: mergers. Our universe is a dynamic and evolving place, and galaxies are not isolated islands. Over cosmic time, galaxies interact, collide, and merge with one another in a process of hierarchical assembly. When two galaxies merge, their central supermassive black holes are set on an inevitable collision course. They begin a long, slow gravitational dance, orbiting each other for millions of years. As the two black holes orbit, they lose energy by stirring up the surrounding stars and gas, causing their orbit to shrink. They get closer and closer, spiraling inward in a cosmic waltz that gets faster and more violent. In the final moments of this process, the two black holes are moving at a significant fraction of the speed of light. As they merge, they radiate an immense amount of energy away, not as light, but as powerful ripples in the fabric of space-time itself, gravitational waves. This is one of the most energetic events in the universe since the Big Bang, a cataclysm that sends shudders through the cosmos. The detection of these gravitational waves by observatories like LIGO and Virgo has opened up an entirely new way to study the origin and growth of black holes. For the first time, we are not just inferring their presence, but directly listening to the sound of their mergers. Each detected event provides a wealth of information. We can measure the masses of the two initial black holes and the mass of the final merged black hole. This allows us to directly confirm that black holes do indeed merge and grow, and it helps us build a census of the black hole population throughout the universe, testing our theories about their formation and evolution. These merger events are a fundamental engine of growth. A collision between a million solar mass black hole and another of a similar size can instantly create a 2 million solar mass black hole, doubling its size in a cosmic instant. This process, repeated over billions of years as galaxies continue to assemble, is a powerful and efficient way to build the truly colossal black holes, those weighing billions of solar masses that we see at the heart of the largest galaxies in the modern universe. The story of the origin of supermassive black holes is therefore a combination of nature and nurture. The formation of initial seeds, followed by a lifetime of growth through both steady accretion and violent, spectacular mergers. While stellar mass and supermassive black holes are born from the processes of cosmic evolution, there is a third, more speculative category, whose origins would be far more ancient. These are primordial black holes, hypothetical objects that would not have formed from the collapse of a star, but from the extreme conditions of the very early universe itself. In the first fractions of a second after the Big Bang, the universe was an incredibly hot and dense soup of energy and exotic particles. The density was far greater than anything found inside a star today, and it was not perfectly uniform. The theory suggests that in regions where the density was significantly higher than average, the intense pressure and gravity of the primordial plasma could have been enough to trigger a direct gravitational collapse. These density fluctuations could have spontaneously compressed pockets of energy into black holes of a vast range of possible masses. Unlike stellar black holes, which have a lower mass limit of about 3 solar masses, primordial black holes could be much smaller. They could theoretically have the mass of a mountain, a car, or even less. They would be tiny, ancient relics of the universe's fiery birth, scattered throughout the cosmos. The existence of primordial black holes is a tantalizing but unproven idea. If they exist, they could help solve some of the biggest mysteries in cosmology. For example, some scientists have proposed that primordial black holes could be a candidate for dark matter. This mysterious, invisible substance makes up about 85% of the matter in the universe, and its gravitational effects are essential for holding galaxies and galaxy clusters together. Since primordial black holes interact with their surroundings almost exclusively through gravity, a large population of them could provide the missing mass we are looking for without being easily detectable through light. However, the search for these ancient objects has so far come up empty. Astronomers have used various methods to look for their effects, such as searching for the gravitational lensing of starlight as a tiny black hole passes in front of a distant star, or looking for the faint glow of Hawking radiation that very small black holes are predicted to emit. So far, these searches have placed strong constraints on how many primordial black holes of certain masses could exist, ruling them out as the sole component of dark matter in many mass ranges. Nevertheless, the possibility remains open, a fascinating reminder that the origins of black holes might be even more diverse and more deeply connected to the beginning of time than we currently imagine. Black holes are born from the most complex and violent events in the cosmos, like the collapse of a gigantic star. The material that forms them is a messy and complicated mixture, possessing intricate magnetic fields and a unique history. Yet, once the black hole forms and settles down, all of this complexity is wiped away. A remarkable concept in physics known as the no-hair theorem states that a stable black hole is an object of profound simplicity. It can be completely described by just three properties: its mass, its electric charge, and its angular momentum, or spin. All other information is lost forever behind the event horizon. This idea, championed by physicists like John Wheeler, is what makes black holes such perfect theoretical objects. A star has a complex chemical composition, a turbulent surface, and a tangled magnetic field. A planet has weather, geology, and countless surface features. A black hole, in contrast, is stripped bare of all such details. Two black holes with the same mass, charge, and spin are absolutely identical, regardless of what star they formed from. This simplicity is both elegant and deeply unnerving, as it implies that information about the black hole's creation is irretrievably destroyed. Of these three properties, mass and spin are the most important for the black holes we observe in the universe. The mass determines the size of the event horizon and the strength of its gravitational pull. The spin is a measure of how fast the black hole is rotating. Just as a spinning ice skater pulls in their arms to spin faster, the collapsing star conserves its angular momentum, resulting in a black hole that can rotate at incredible speeds. This spin has a profound effect on space-time, dragging it along like a vortex. Electric charge is thought to be negligible for most black holes, as they would quickly neutralize themselves. So, despite their terrifying reputation, black holes are the simplest macroscopic objects in the entire universe. They are pure gravity, shaped only by their total mass and their rotation. This radical simplicity allows physicists to calculate their properties with precision, making them perfect laboratories for testing Einstein's theory. The no-hair theorem paints a picture of a cosmic beast elegant in its minimalism, a perfect void defined not by what it is made of, but by the fundamental influence it has on space-time. At the very heart of a black hole is the event horizon. This gravitational boundary is a one-way door. Anything that crosses it is trapped forever. Imagine an astronaut falling toward a black hole. From a distance, time would appear to slow down for them. But according to relativity, the astronaut wouldn't notice crossing the event horizon. The consequences, however, are absolute. Inside, all paths lead inward, towards the singularity. The size of the event horizon depends on the black hole's mass. This boundary is the ultimate veil, hiding the black hole's secrets from the universe. No information can ever escape to tell the tale. If you could pass through the event horizon, your journey would lead you to the singularity. According to general relativity, the singularity is the black hole's center, where all matter is crushed into zero volume, resulting in infinite density and gravity. Here, the laws of space and time break down. Physicists believe understanding the singularity requires a theory uniting general relativity with quantum mechanics. This quantum gravity theory might reveal the singularity as an exotic quantum state of matter. For now, the singularity remains the ultimate prison for matter and our knowledge. Rotating black holes possess a fascinating region just outside the event horizon, known as the ergosphere. It actively drags space-time around it, an effect called frame dragging. Everything within the ergosphere is forced to move with the black hole's rotation. The Penrose process suggests energy can be extracted from a rotating black hole. By carefully arranging trajectories, escaping objects can emerge with more energy, stolen from the black hole's rotation. This powers energetic phenomena like plasma jets seen blasting from supermassive black holes. Complex magnetic fields act as a natural Penrose process, flinging material at near light speed. The most common type of black hole found scattered throughout the cosmos is the stellar mass black hole. As their name suggests, these are the direct descendants of stars, the compact corpses left behind after a massive star has died in a fiery supernova explosion. They represent the final stage of life for the universe's biggest and brightest stars. Their mass typically ranges from about 3 times the mass of our Sun, the minimum required to overcome neutron degeneracy pressure, up to several tens of solar masses. Any larger, and the star would likely be so massive as to be unstable during its lifetime. Stellar mass black holes are relatively small in physical size. A black hole with 10 times the mass of our Sun, would have an event horizon with a radius of only about 30 kilometers. You could fit this entire object within the boundaries of a major city. Despite their small size, their gravitational influence is immense. They are the silent predators of the galaxy, wandering through space after being kicked out by the supernova explosion that created them. Most are likely isolated and invisible, making them incredibly difficult to detect. We only find them when they happen to be in a binary system with a normal star. When a stellar mass black hole has a close stellar companion, its powerful gravity can pull material from the outer layers of the other star. This stolen gas forms a swirling, superheated structure around the black hole called an accretion disk. As the gas spirals inward, friction heats it to millions of degrees, causing it to emit intense X-rays. It is this X-ray signature that allows astronomers to find these hidden objects. Systems like Cygnus X1, one of the first and most famous black hole candidates discovered, are precisely this kind of X-ray binary. By studying the orbit of the visible companion star, we can calculate the mass of the invisible object and confirm that it is too heavy to be a neutron star. Our own Milky Way galaxy is estimated to contain as many as 100 million stellar mass black holes, born from generations of massive stars over billions of years. Most of these are floating through the interstellar darkness completely alone. However, the recent advent of gravitational wave astronomy has given us a new way to find them. Observatories like LIGO and Virgo can detect the ripples in space-time produced when two of these stellar mass black holes in a binary system finally spiral into each other and merge. These detections are giving us our first true census of this hidden population of cosmic ghosts. Between stellar mass and supermassive black holes lies the elusive intermediate mass black hole, or IMBH. Ranging from 100 to 100,000 times the mass of our Sun, they're the missing link in the cosmic black hole family. Predicted by black hole growth theories, they bridge the gap between stellar death and supermassive galactic behemoths. Finding them has been a major challenge. Expected to lurk in dwarf galaxies or globular clusters, they're harder to spot. IMB8s are likely seeds for supermassive black hole growth in the early universe. Theories suggest dense cores of early globular clusters provided the perfect formation environment. Compelling evidence came from LIGO, which observed a black hole merger creating a 142 solar mass black hole, the first definitive IMBH detection. At the top of the black hole mass ladder are the undisputed kings of the cosmos, the supermassive black holes. These are the giants that reside at the gravitational heart of almost every large galaxy, including our own Milky Way. Their masses are staggering, ranging from a few 100,000 to tens of billions of times the mass of our Sun. Unlike their stellar mass cousins, they are not the remnants of a single star. Their origin is a complex story of cosmic evolution, likely involving the merging of smaller black holes and the continuous consumption of gas, dust and stars over billions of years. They are as old as the galaxies they inhabit. The presence of a supermassive black hole has a profound influence on its host galaxy. While its direct gravitational pull only dominates a relatively small central region, its role as a cosmic engine can be felt across the entire galactic disk. When a supermassive black hole is actively feeding, the material in its accretion disk becomes incredibly hot and luminous, turning the galactic center into a quasar or an active galactic nucleus. This process can release more energy than all the billions of stars in the galaxy combined. This immense energy output can drive powerful winds and jets that blast out from the galaxy's core. These galactic outflows act as a form of feedback, regulating the growth of the galaxy itself. The powerful jets can heat up or blow away the cold gas clouds throughout the galaxy, which are the raw material needed to form new stars. This process can effectively shut down star formation, preventing the galaxy from growing too large. This intimate connection between the growth of a central black hole and the evolution of its host galaxy is one of the most important discoveries in modern astrophysics. It shows that these giants are not just passive objects, but active participants that help to sculpt the universe we see today. Our own supermassive black hole, named Sagittarius A*, is a relatively peaceful giant at the moment. It weighs about 4 million solar masses and its event horizon has a radius of about 12 million kilometers. We can't see it directly, but we can track the orbits of stars that whip around it at incredible speeds, providing definitive proof of its existence and mass. By studying these stars, we get a close-up view of the extreme gravitational environment at a galaxy's heart. These galactic centers, governed by their supermassive hearts, are the grand arenas where the laws of gravity are tested in their most extreme form. Just outside a black hole's event horizon is the photon sphere. Here, gravity is so strong that photons can orbit. A beam of light at the right angle would be trapped in a circular path. Light leaving the back of your head would travel around the black hole and back to your eyes. This sphere is crucial to what we see of a black hole. Light from behind it is bent, creating the black hole's famous shadow. The bright ring isn't the event horizon, but the accretion disk viewed through the photon sphere's lens. Observing this ring allows scientists to measure the black hole's mass and spin. For centuries, black holes were purely theoretical objects. They emit no light, making them impossible to see directly. The answer lies in seeing its silhouette cast against the bright backdrop. This shadow is a consequence of the black hole's extreme gravity bending light. In 2019, the Event Horizon Telescope unveiled the first image of a black hole shadow in the galaxy M87. The image showed a dark central region surrounded by a glowing ring of light. It was a stunning visual confirmation of Einstein's predictions, allowing us to finally see the unseeable. Imagine space-time as a flat-stretched rubber sheet. A planet like Earth would create a small dimple in this sheet. This is what a black hole does to the fabric of space-time. It creates the ultimate gravitational well, the deepest and steepest one possible in the universe. Near a black hole, gravity dictates the motion of everything, from massive stars to the tiniest particles of light. This concept of a gravitational well helps us understand why escape is so difficult. Inside the event horizon, the well is effectively a bottomless pit from which no escape is possible. It is a direct consequence of mass warping geometry, as described by Einstein's general relativity. It is a journey into a region where the familiar rules of our universe are twisted into a new and strange reality. One of the most unsettling effects of a black hole's gravity is spaghettification. This describes what would happen to any object, including a human body, as it falls into a black hole. The gravitational pull is not uniform, changing dramatically over short distances. Imagine an astronaut falling feet first toward a stellar mass black hole. The immense tidal force would stretch their body. The object would be stretched and thinned, much like a piece of spaghetti. Interestingly, for a supermassive black hole, the story is different. An astronaut could cross the event horizon completely intact, facing inevitable stretching much later. One of the most mind-bending consequences of Einstein's theory is that gravity affects time. Near a black hole, this becomes extreme. Time slows for anyone near it. Imagine two observers, one orbiting a black hole safely and another closer to the event horizon. Time is relative. Its passage depends on your gravitational environment. An astronaut could orbit a black hole for a short time and return to find centuries have passed. Time would stop at the event horizon relative to a distant observer. Time becomes a local quantity, distorted by gravity. Let us now follow a brave or perhaps foolish explorer on their final journey as they decide to cross the event horizon of a supermassive black hole. As we have learned, choosing a supermassive one allows them to pass the threshold without being immediately torn apart by tidal forces. From their own perspective, the moment of crossing the event horizon would be surprisingly uneventful. There is no physical barrier, no wall to crash into, no siren to warn them of their irreversible mistake. They would simply float across this invisible line in space, in a state of perfect freefall, feeling no forces at all. This is a key prediction of Einstein's principle of equivalence, which states that the effects of gravity are indistinguishable from the effects of acceleration. In freefall, you are weightless and you feel no gravity. An astronaut floating inside the International Space Station feels weightless, even though Earth's gravity is still very strong at that altitude. Similarly, our explorer in free fall towards the black hole would feel nothing at the moment of crossing. The laws of physics in their immediate vicinity would seem perfectly normal. They could shine a flashlight, and the beam would appear to travel away from them at the speed of light, just as it always does. However, despite the lack of immediate sensation, a fundamental and irrevocable change has occurred. The very nature of space and time has been swapped. Outside the black hole, you have freedom of movement in 3 spatial dimensions: up and down, left and right, forward and backward. You are, however, forced to travel in one direction through time into the future. Once our explorer crosses the event horizon, this reality is flipped. The direction toward the singularity, which was once a direction in space, now becomes a direction in time. It becomes the future. It is as unavoidable as tomorrow. This means that inside the event horizon, our explorer loses their freedom of movement. They can no longer choose to move away from the singularity. Every possible path, every direction they could fire their rockets, every way they could turn, inevitably leads them closer to the central point of infinite density. Trying to accelerate away from the singularity would be as futile as trying to accelerate into the past. The journey to the center is now a matter of time, not distance. Their fate is sealed, and their final moments are ticking away as they are drawn inexorably toward their doom at the heart of the black hole. The experience of crossing the event horizon is profoundly different for someone watching from a safe distance. Let us return to the observer in the faraway spaceship, monitoring their friend's journey into the black hole. As the explorer's ship approaches the event horizon, the observer would witness the strange effects of gravitational time dilation and gravitational redshift becoming more and more extreme. The clock on the falling ship would appear to tick slower and slower, approaching a complete stop as it nears the boundary. Any signals sent back would take longer to arrive and be stretched to lower and lower frequencies. A video feed from the explorer's ship would play out in agonizing slow motion. Their movements would seem to take an eternity. The light from the ship's engines and cabin would become dimmer and redder, shifted down the electromagnetic spectrum by the intense gravity. As the ship gets infinitesimally close to the event horizon, the observer would see its image seem to freeze. It would be forever poised at the edge, never quite crossing. The image would become so red-shifted and dim that it would eventually fade from view, its light stretched beyond the ability of any instrument to detect. The explorer would appear to be frozen in time for all eternity. This frozen farewell is a consequence of the infinite time dilation at the event horizon from an external frame of reference. The light emitted by the falling object at the exact moment it crosses the horizon would take an infinite amount of time to climb out of the gravitational well and reach the distant observer. Therefore, the observer never actually sees the object cross the boundary. From our perspective in the outside universe, nothing ever truly finishes falling into a black hole. It is simply added to a frozen, ghostly layer of information plastered on the surface of the event horizon. This raises a fascinating paradox. For the falling explorer, the journey across the event horizon and to the singularity takes a finite amount of time. For the outside observer, this event never happens. Both perspectives are equally valid according to the theory of relativity. This discrepancy lies at the heart of a deep puzzle in physics known as the black hole information paradox. What happens to the information contained within the object that falls in? Is it lost forever at the singularity, or is it somehow preserved on the event horizon, as the outside observer's perspective might suggest? This question remains one of the greatest unsolved mysteries in science. A black hole's gravity doesn't just trap light that gets too close, it also bends the path of any light that passes nearby. This phenomenon, predicted by Einstein's general relativity, is called gravitational lensing. A black hole acts like a powerful, albeit imperfect, lens in space. Its immense mass warps the space-time around it, forcing light rays to follow curved paths. This effect provides astronomers with another powerful tool to detect and study black holes and other massive objects, even when they are completely invisible. It allows us to see the shape of space-time itself. Imagine a distant star, or galaxy that lies directly behind a black hole from our point of view. As the light from this distant object travels towards us, it passes through the warped space-time around the black hole. The light rays that pass above the black hole are bent downwards, while the rays that pass below are bent upwards. This can create multiple distorted images of the background object. If the alignment is absolutely perfect, the light from the background star will be smeared into a complete circle known as an Einstein ring. More commonly, we see multiple arcs or duplicate images of the same distant galaxy. This effect is not unique to black holes. Any massive object, like a galaxy or a cluster of galaxies, can act as a gravitational lens. However, the lensing caused by a single black hole is particularly strong and compact. The most extreme example of this is the black hole's shadow. The bright ring of light seen in the Event Horizon Telescope images is a direct result of gravitational lensing. It is the light from the hot gas behind and around the black hole, bent into a near-perfect circle by the black hole's gravity as it passes through the photon sphere. This provides a direct visual confirmation of light bending in an extreme gravity environment. Gravitational lensing is also used to hunt for smaller, isolated black holes wandering through our galaxy. A technique called microlensing looks for the temporary brightening of a background star. If a wandering black hole passes almost directly in front of a distant star, its gravity will briefly focus the star's light, causing it to appear brighter for a few days or weeks. By monitoring millions of stars, astronomers can look for these characteristic brightening events, which can reveal the presence of an otherwise invisible stellar mass black hole. It is like using the universe as a giant detective's magnifying glass to find its most elusive inhabitants. While a black hole itself is dark, the region immediately surrounding it can be one of the brightest and most violent places in the entire universe. This is because black holes are rarely alone in space. They are often surrounded by gas, dust, and stars. As this material is drawn in by the black hole's powerful gravity, it doesn't fall straight in. Due to the conservation of angular momentum, the material spirals inwards, forming a flattened, rotating structure called an accretion disk. This disk is a cosmic traffic jam of matter on a one-way trip to oblivion, and it is a place of incredible energy and light. As the gas and dust in the accretion disk swirl closer to the black hole, they move at incredible speeds, approaching the speed of light near the inner edge. The different layers of the disk rub against each other, creating immense friction. This friction heats the material to millions or even billions of degrees, far hotter than the surface of any star. This superheated plasma glows with ferocious intensity across the entire electromagnetic spectrum, from low-energy radio waves to the most energetic X-rays and gamma rays. The accretion disk is the final, brilliant scream of matter before it crosses the event horizon and is lost forever. The efficiency of this process is astounding. A black hole's accretion disk can convert matter into energy with an efficiency of 10% or more. This is more than 10 times more efficient than the nuclear fusion that powers stars like our Sun. This incredible energy conversion is what makes active galactic nuclei and quasars shine so brightly. A single quasar powered by a supermassive black hole feeding on its accretion disk can easily outshine its entire host galaxy, which contains billions of individual stars. It is the most efficient engine for generating light known in the universe. In many cases, not all of the material in the accretion disk makes it into the black hole. Powerful magnetic fields tangled within the rotating disk can act like cosmic accelerators. They can capture some of the superheated plasma from the inner edge of the disk and fling it outwards in two powerful narrow beams, or jets. These relativistic jets shoot out from the poles of the black hole at nearly the speed of light, traveling for thousands or even millions of light years into intergalactic space. They are a dramatic testament to the fact that the region near a black hole is not just a place of consumption, but also a powerful cosmic engine. What would our unfortunate explorer see in the final moments of their journey inside the event horizon? This is a realm of pure speculation, guided by the strange mathematics of general relativity. As they fall towards the singularity, Their view of the outside universe would become bizarrely distorted. The light from the entire history of the external universe, from the Big Bang to its ultimate end, would theoretically be visible to them in a rapidly accelerating flash. The event horizon behind them would appear to shrink to a small bright point, a single window onto the universe they left behind. Looking forward in the direction of the singularity, they would not see a dark point. The singularity itself is not a place you can see. It is an inevitable moment in your future. The view in all directions would be dominated by the intensely blue-shifted light of stars and matter that fell into the black hole earlier. This light, trapped within the event horizon and falling alongside our explorer, would become incredibly bright and energetic. The sky inside a black hole would not be black, but a chaotic and blinding inferno of high-energy radiation converging from all sides. The very concepts of space and time would become twisted beyond recognition. As our explorer gets closer to the singularity, the tidal forces would become infinitely strong. The spaghettification process would reach its ultimate conclusion, stretching not just their body, but the very atoms they are made of into a one-dimensional line. Space-time curvature would become infinite. The laws of physics as we understand them would cease to have any meaning. The journey ends where space and time themselves end, crushed out of existence in an instant of infinite density. This description is, of course, based on a theory, general relativity, that we know is incomplete. To truly know what happens at the singularity, we would need a theory of quantum gravity. Perhaps quantum effects would prevent the formation of an infinitely dense point, replacing it with something else, a Planck star or a fuzzball. Perhaps the singularity is a gateway to another universe. But without a complete theory and with no way for information to escape, the true nature of the final moments inside a black hole remains the greatest and most well-kept secret in the entire cosmos, forever hidden behind the veil of the event horizon. Once an object crosses the event horizon, its fate is sealed. The laws of physics as we currently understand them offer no possibility of escape. To leave the region inside the event horizon would require traveling faster than the speed of light, a universal speed limit that appears to be fundamental to the structure of our reality. The geometry of space-time inside the black hole is so warped that all paths lead to the singularity. There are, well, simply no directions that point outwards. Firing your rocket engines, no matter how powerful, would only hasten your demise, accelerating you towards the singularity even faster. This one-way nature of the event horizon is a core feature of a black hole. It is a perfect trap, a cosmic prison from which there is no parole. This concept has troubled physicists for decades because it seems to violate a fundamental principle of quantum mechanics, the conservation of information. Quantum theory suggests that information can never be truly destroyed. It can be scrambled and rearranged, but the fundamental details about a system's state should always be preserved. However, a black hole seems to swallow information, and if the black hole later evaporates via Hawking radiation, that information appears to be lost forever. This conflict between general relativity and quantum mechanics, known as the black hole information paradox, is a deep and unsolved problem. It suggests that our understanding of black holes is missing a crucial piece. Some physicists, like Stephen Hawking, initially argued that information was indeed lost, forcing a rewrite of quantum mechanics. Later, he and others proposed that perhaps the information isn't lost, but is somehow encoded in the subtle quantum properties of the outgoing Hawking radiation. Or perhaps it is stored on a firewall at the event horizon. These ideas are at the cutting edge of theoretical physics. For any practical purpose, however, the conclusion remains the same. A black hole is a point of no return. There are no secret escape routes, no theoretical loopholes that an astronaut could exploit. While physicists debate the ultimate fate of information on a quantum level, the fate of any macroscopic object is clear and unambiguous. The journey near a black hole is a journey into the most extreme environment the universe has to offer. A place where time and space are warped, matter is destroyed, and from which, once you have entered, there is absolutely no coming back. For over a century, the black hole existed as a ghost in our theories, a solution to Einstein's equations that even he doubted. We saw stars orbiting nothing and detected X-rays from matter being consumed, but we had never seen one. In April 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole and its shadow. The target was the supermassive black hole at the heart of Messier 87, a giant elliptical galaxy 55 million light-years away. They synchronized a global network of 8 high-altitude radio telescopes, creating an Earth-sized observatory. It was a glowing asymmetrical ring of light surrounding a perfect circle of darkness, the shadow of a giant. The image was a stunning vindication of Albert Einstein's general theory of relativity. The image transformed the black hole from a theoretical concept into a tangible, observable entity. While the first black hole image came from a distant galaxy, we have one in our own backyard, at the center of the Milky Way, Sagittarius A*. Located 27,000 light-years from Earth, its true nature was long obscured. Astronomers used infrared and radio telescopes to peer through cosmic fog. Decades of tracking stars closest to the galactic center provided definitive proof. Stars were found whipping around a central point at incredible speeds. The star S2 completes an orbit every 16 years, traveling at 2% of light speed at its closest approach. Calculations revealed these stars orbit an object 4 million times the mass of our Sun, within a space smaller than our solar system. Only a supermassive black hole could contain such mass in that volume. This earned Genzel and Ghez the 2020 Nobel Prize in Physics. In 2022, the first image of Sagittarius A** confirmed a dark shadow surrounded by a glowing ring. For most of history, we studied the universe by looking at it. But in 2015, a new window opened. We could listen. Scientists at LIGO announced the first direct detection of gravitational waves, ripples in space-time. These waves, predicted by Einstein, are generated by violent events like colliding neutron stars or black holes. The first signal stretched LIGO's arms by less than a proton's width, a feat of engineering. It was the sound of 2 black holes merging, converting mass into gravitational energy. LIGO and Virgo have since detected dozens of these cosmic symphonies, studying black holes invisible to telescopes. Our galaxy is a dynamic and sometimes violent place. When a massive star explodes as a supernova, the explosion is rarely perfectly symmetrical. This asymmetry can give the resulting object a powerful kick, sending it flying through space at hundreds of kilometers per second. This means that our Milky Way is likely teeming with millions of rogue black holes moving silently through the interstellar darkness. Because they are isolated and invisible, finding these solitary wanderers is one of the greatest challenges in astronomy. For years, the existence of rogue black holes was purely theoretical. We knew they must be out there, but we had no way to see them. They don't have a companion star to steal gas from, so they don't light up as bright X-ray sources. They are simply dark, compact objects adrift in the void. The only way to detect them is through their gravity alone. One of the most promising methods is gravitational microlensing. This technique involves monitoring millions of background stars, looking for a rare, brightening event. If a rogue black hole passes in front of a distant star, its gravity will act as a lens, magnifying the starlight. This lensing event is unique. Unlike lensing caused by a star, a black hole is dark, so the background star brightens without changing color. The duration can help determine the mass of the object. In 2022, astronomers announced the first detection of a solitary stellar mass black hole. Using data from multiple telescopes over several years, they observed a microlensing event that lasted very long, indicating a massive, compact object. Their calculations revealed a rogue black hole of 7.1 solar masses, located about 5,000 light-years away. This groundbreaking discovery was the first of its kind, confirming that this hidden population exists. It opens up a new field of study, allowing us to estimate how many cosmic ghosts are out there. Some estimates suggest 100 million in our galaxy alone. These objects represent a significant component of our galaxy's mass. Finding them through microlensing is a painstaking process, but it's the only way to shed light on these dark nomads. Black holes were thought to be simple, just mass, spin, and charge. But quantum theory says information can't be destroyed, leading to the black hole information paradox. New ideas like quantum hair suggest black holes might subtly imprint information on space-time. hinting that what falls in isn't truly lost. Astronomers now observe stars being torn apart by black holes, tidal disruption events, turning theory into reality. In 2019, we saw a star spaghettified in real time, revealing the chaotic process as stellar debris flares and forms an accretion disk. These events let us study black holes feeding and growing, transforming a gruesome prediction into a powerful tool for exploring the universe. Astronomers are finding the smallest and largest black holes ever, like the Unicorn, just 3 solar masses, and ultra-massive giants with billions of solar masses. These extremes challenge our theories of star death and galaxy growth. Studying them helps us understand the full range of black holes shaping the cosmos. Light can't escape a black hole, but X-ray echoes from behind one have been detected, confirming Einstein's predictions. These echoes, bent by gravity, let us map the environment just outside the event horizon. It's a new way to study black holes' properties, using light as a probe in the most extreme conditions. Stephen Hawking showed black holes aren't completely black. They emit faint Hawking radiation due to quantum effects. This process is slow, but it means black holes can eventually evaporate. While we haven't seen Hawking radiation from space, lab analogues support the theory that even black holes must fade away. We've journeyed from dark star theories to real images, uncovering black holes' roles as cosmic engines and laboratories for extreme physics. Black holes challenge our understanding of space, time, and information, revealing how much we still don't know. The map is drawn, but the greatest mysteries and discoveries await us in the darkness ahead. Section 2. Telescopes of the future will allow us to see the universe in new and better ways. Future telescopes are designed to be bigger, sharper, and more sensitive than ever before. On the ground, giant optical telescopes are being constructed. The Event Horizon Telescope, which gave us our first black hole image, is also evolving. This will allow them to create the first real-time movies of matter swirling around a black hole. Perhaps the most exciting frontier is the future of gravitational wave astronomy. The next great leap will be to take our detectors into space. These future observatories working together will give us a complete and holistic view of black holes. By combining the sound and the light from these cosmic cataclysms, we will unlock the secrets of black holes. Section 3, the quantum enigma inside the information paradox. Beyond the reach of even our most advanced future telescopes lies a deeper, more fundamental mystery. This is the realm where the two great pillars of modern physics, general relativity and quantum mechanics, collide. The most famous battleground in this conflict is the black hole information paradox. General relativity paints a picture of a black hole as an information incinerator, a place where the unique details of everything that falls in are wiped from existence at the singularity. Quantum mechanics, on the other hand, holds as a sacred principle that information can never be truly destroyed. One of these theories, as we currently understand it, must be wrong, or at least incomplete. Solving this paradox is one of the single most important goals in all of theoretical physics. It is the key that could unlock the door to a unified theory of quantum gravity, a theory of everything that can describe the universe at both the largest and smallest scales. Theorists are exploring a host of mind-bending ideas to resolve the conflict. One concept is the holographic principle, which suggests that all the three-dimensional information of an object that falls into a black hole is somehow stored on the two-dimensional surface of its event horizon, like a cosmic hologram. The information isn't lost, it's just encoded in a different, scrambled form. Another intriguing idea is that of a firewall. This radical proposal suggests that the event horizon is not an empty, unremarkable place as Einstein predicted. Instead, it could be a searing, hot wall of high-energy particles that would instantly destroy anything attempting to cross it. In this scenario, the information never truly enters the black hole, thus avoiding the paradox of its destruction at the singularity. This would, however, violate Einstein's principle of equivalence, the idea that an observer in freefall feels no gravity. It presents a stark choice between the core principles of our two most successful theories. A third possibility, perhaps the most profound, is that our very notions of space and time are not fundamental but are emergent properties of something deeper. Some theories, like string theory, propose that the singularity is not a point but a fuzzball of vibrating strings which stores information in its complex quantum state. Others suggest that space-time itself is built from a network of quantum connections, and that inside a black hole, this network is simply reconfigured, not destroyed. These ideas are at the very frontier of human thought, pushing the limits of our imagination as we grapple with the ultimate fate of information in our universe. Section 4. Beyond black holes, wormholes, white holes and other possibilities. The mathematics of general relativity is a rich and complex landscape, and black holes are not the only exotic solution that can be found within its equations. Lurking in the same theoretical territory are other, even more speculative cosmic objects. One of the most famous of these is the wormhole, or Einstein-Rosen bridge. A wormhole is a hypothetical shortcut through space-time, a tunnel that could connect two distant points in our universe, or even connect our universe to another one entirely. In theory, a black hole's singularity could be connected to the singularity of another object, forming such a bridge. However, the wormholes predicted by classical general relativity are thought to be incredibly unstable. They would collapse in on themselves the instant they formed, making them impossible to traverse. To keep a wormhole open would require a form of exotic matter, a substance with negative mass or negative pressure, which has never been observed and may not exist. While wormholes remain a staple of science fiction, providing a convenient way to travel across the galaxy, their physical reality is highly questionable. They are a mathematical possibility that nature may have chosen not to create. Another strange cousin of the black hole is the white hole. A white hole is the time-reversed version of a black hole. While a black hole is a region of space-time that you can only enter and never leave, a white hole is a region that you can only leave and never enter. It would be an object that spews matter and energy out into the universe, but nothing could ever cross its event horizon from the outside. Some physicists have speculated that the Big Bang itself might have been a kind of white hole event. However, like wormholes, there is no known physical process that could form a white hole, and we have never observed anything that behaves like one. These concepts, along with others like naked singularities, singularities without an event horizon to hide them, force us to consider the absolute limits of physical law. They are the what-ifs of cosmology. Do they represent real possibilities for our universe, or are they simply mathematical artifacts, pathways in the equations that nature has forbidden? The study of black holes naturally leads us to these more fantastical ideas because they all spring from the same root, the extreme warping of space-time. Answering whether these objects are real or fictional will require a deeper understanding of quantum gravity and the ultimate rules that govern our cosmos. Section 5. Why we keep looking. The human quest for the ultimate truth. Why do we invest so much into studying these dark, distant and dangerous objects? The quest to understand black holes is a fundamental part of the human endeavor to understand our place in the universe. Black holes represent the ultimate frontier of our knowledge. When we study black holes, we are probing the very nature of space, time, gravity and information. They will form the basis of the next revolution in physics, one that could reshape our entire conception of the cosmos. It is a profoundly hopeful expression of what humanity can achieve when we unite to solve the great mysteries of our existence. In the end, we keep looking into the darkness, because it is in our nature to seek the light of understanding. Our journey to understand the black hole is a journey that is far from